Hello everyone, I'm Yunan Gao from Dalhousie University. In this paper, we designed Limpoziv compression-based indexes to compute the matching statistics. The matching statistics of a pattern P of length m with respect to a text T is an array of m integers, such that the ith entry in the array stores the length of the longest prefix of substring Pim. That occurs in T. Here is the example. The text stores AAA, BBB, CC, and the query pattern is CCABB. The corresponding matching statistics is an array of 5 integers. You can see that the prefix CC of P appears in the text, but CCA does not. Therefore, the first entry of the array stores the length of prefix CC, which is 2. There are several results on this problem. For a text of n characters, we can build a suffix-treated structure augmented with the suffix links on the tree nodes. Note that sigma in the query time represents the alphabet size. In the paper Spare 2010, they designed fully compressed indexes using a little more than n log sigma bits. In the genomic databases, texts are always massive and highly repetitive. The compressed indexes based on statistical entropy may not compress the original text efficiently. Benet et al. Showed that a Run-Lens-Boros-Wheeler transform can be augmented to compute the matching statistics. Suppose there is a S of n words of space data structure to support retrieving any substring of length L in f of n plus L time, then their data structure would use O of S of n plus R words of space and support computation in O of m f of n time. Here R is the number of runs in BWT. In this paper, we designed 3 data structures for this problem. All of them are based on Limpoziv parsing. We use Z to denote the number of phrases in the Limpoziv parsing. In the naive method, our data structure uses only O of Z plus S of n words of space. While comparing to the results by Benet et al., our query time has an actual m squared log Z to the epsilon term. Our second solution uses OZ log Z plus S of n words of space, but we managed to improve the actual term to be m squared plus m log Z log Z. Finally, if the alphabet size is constant, we can further improve the actual term in the query time to be m squared. It has been proved that the number of runs in BWT is bounded by O of Z log n squared. Therefore, in theory, all 3 results we designed have more efficient space cost. Before presenting our data structures, we introduced the induced and partner operations using an example. Assume that we are given a text of length 16 as shown above. We partition the text into Limpoziv phrases, and we list the reversed phrases and their corresponding suffixes in the table below. So based on the reversed phrases and the suffixes, we construct Patricia Troy respectively. We denote the 2 Patricia Troys by trev and tserf. In addition, we construct a grid of J points. On the grid, we list the reversed phrases along the x-axis and the suffixes along the y-axis. Both are sorted by alphabet order. We draw a point xy on the grid if and only if the string concatenated by the x phrase and the y suffix appears somewhere in the original text. Note that each leaf node in the trees trev and tserf corresponding to a point on the grid. A node v on tree trev and a node u on tree tserf are induced together if v and u have the common leaf descendant. Regarding the common leaves on different trees, we meant that both leaves corresponding to same point on the grid. For example, under the node V on trev and under the node U on tserv, there is a leaf node colored in green. Given a node V on trev and a node U on tserv, operation partner of V over U returns the lowest ancestor node of U that is induced with V. In this example, node V on trev and U on tserv are not induced with each other, but the parent of U and V has the same leaf descendant colored in black. Therefore, partner V over U returns the parent node of U. If we concatenate the path string of V and its partner, we got a string AB. The partner relationship tells that AB is a substring of the text, but ABA does not. The partner operation can be implemented by 2D orthogonal range successor or predecessor queries on the grid. We first discussed the naive method. We divide the query pattern into n-1 pairs of prefixes and suffixes and operate the query procedure upon each pair of them. Consider the S pair P1i and Pi plus 1i. We search for their locus, loci 1 of I and loci 2 of I over both trees. For each ancestor node U of loci 1 of I, we find its partner over loci 2 of I. Then we can use the sum of the lengths of the path strings of U and its partner to update the entries in the matching statistics. As you can see that as the node U go upwards, its partner go downwards. After processing all n-1 pairs of prefixes and suffixes, we finish computing the matching statistics. In total, we operate all of m² partner operations. Recall that there are z points on the grid. If only O of z words of space is allowed, each partner operation takes log z to the epsilon time. In addition, finding all n-1 pairs of locus takes O of m² plus mf of n time. Therefore, the overall query time and the space cost are as shown in the bottom. Before showing the second method, we introduce LPMAM, short for locally potential maximum exact matches. Suppose that the th prefix is ABWWZ, and its corresponding suffix starts with XYYCD. The path string of loci 1 is ZWWB, while the path string of loci 2 is XYYC. Clearly, the pattern is split by the phase boundary between Z and X. Suppose that we find a substring of T that crosses the same phase boundary, and such substring matches the query pattern as this. Since the matched substring WWZXYY cannot be extended to either the left or to the right, we call it LPMAM. The left endpoint of LPMAM corresponds to a node on tree trev, while the right endpoint of LPMAM corresponding to a node on tree tserv. We observe that each of the corresponding nodes has at least 2 branches or 2 descendant leaves. Later, we can use this observation to find each LPMAM efficiently. For a query pattern of length m, there are at most O of m² different LPMAMs. In algorithm 2 of this paper, we show that once we found all these awk LPMAMs, we can compute the matching statistics within m plus oak time. In this way, we don't need to find the partner node for each ancestor node of loci 1, thereby improve the overall running time. In the second method, again, we consider the S pair of prefix and suffix that the query pattern is split into. Our goal is to find all the LP-MEMS between loci 1 and loci 2. This time we apply a heavy path decomposition on tsurf. For each f between 1 and k, we use WF to denote the light nodes that are above loci 2 of I. Note that k is no larger than log z, and we use HP leaf of WF to denote the leaf node on the heavy path routed by the WF. Each node TF represents the parent node of WF plus 1. In addition, we use alpha f to denote the partner node of TF over loci 1 of I, and we use beta f to denote the partner node of WF. Lemma 6 in this paper proves that alpha f and its partner over loci 2 of I together induce a LP-MEM, so do beta f and its partner over loci 2 of I. Since there are k pairs of alpha f and beta f, we can find those LP-MEMs by k times of partner queries. This time, we are allowed to use O of z log z words of space for 2D orthogonal range successor and predecessor queries, and each query takes O of log z time, finding all the LP-MEMs starting from either alpha f or beta f takes O of log z time. Another important property given in lemma 7 of this paper tells that if U and V are induced together, and if V stays between WF and TF, then node U must stay between alpha f and beta f, since it remains to find all the LP-MEMs whose starting node is between each pair of alpha f and beta f. To report each of the remaining LP-MEMs in constant time, we need actual work in the preprocessing step. In the preprocessing step, we are only aware of WF and its leaf node on the same heavy path, while all TF, alpha f, and beta f are unknown to us because loci 1 and loci 2 are only given in the query step. In lemma 6 of this paper, we state that for any node U between alpha f and beta f, the partner node of U over loci 2 of I is the same as the partner node over HP leaf of WF, and is also the same as U's partner over TF. Therefore, knowing HP leaf of WF is sufficient. To find a way around the barrier that alpha f and beta f are unknown, we use the induced subtree T-rev of WF introduced in the paper CPM 2018. We refer to the leaf nodes on T-rev that are induced with the light nodes WF in tsurf as special leaves. The induced subtree T-rev of WF are constructed by special leaves and their lowest common ancestors on T-rev. As shown in the picture, the special leaves are marked in orange color, and on the left-hand side, it shows the induced subtree T-rev of WF extracted from T-rev. Both special leaves and their lowest common ancestors are called special node. It has been proved that by summing over all the different light nodes, all induced subtree totally contain O of z log z nodes. Here we can use the observation mentioned before, since the starting node of LP-MEM has at least 2 descendant leaves. Lemma 9 in this paper proves that the starting node of LP-MEM always stays at a special internal node. In the picture, we use the capital letters to represent the special internal nodes. At each special internal node, we store a pointer E2 that points to its partner over the leaf node on the heavy path routed by WF. In this way, once we confirm that a special internal node is a LP_MEM in the query procedure, we can directly access to its partner over loci 2 in constant time without calling the partner operation. As shown in the picture, given a special internal node, say U, on the left tree, we use U prime on the tree tserv to represent U's partner. In addition, each special internal node stores another pointer E0. Pointer E0 can help us find the next LP_MEM above the current node in constant time. So how can we do that? Given a pair of parent and child nodes on the induced subtree, if the child node does not induce with the partner of its parent, then we make the E0 pointer of the child node point to the parent node. For example, O and L are a pair of parent and child nodes. Since L does not induce with the partner of its parent, then we create a green pointer that starts from L and points to O. Well, you might notice that some child nodes are indeed induced with the partner node of its parent, such as the node labeled by X. So what should we do with those nodes? Again, taking node X as example, we found the lowest ancestor of X that has a valid E0 pointer. In the picture, that ancestor node is V, and we make the E0 pointer of X point to V's parent. In this way, every special internal node has a valid E0 pointer, and if we confirm that a node is a starting node of some LP_MEM, then we can immediately find the starting node of the next LP_MEM in constant time following the E0 pointer. Now we return the question left before, how to find the LP_MEMs between beta f and alpha f? Well, beta f and alpha f are not included. Note that the starting node of each such LP_MEM is a special internal node. We first found the lowest special node above beta f in O of log z time using 2D orthogonal predecessor-successor queries. After that, each of those LP_MEMs can be reported in constant time using the E0 and the E2 pointers. After all, we summarize the result of our second method as follows. For the third method, please read the full version of this paper. Finally, we conclude this talk by an open problem. Although the space cost of our data structures are efficient, the m² term in the query time is not exciting. So the open problem we left is, can we achieve O of mf of n computation time using only O of z log z plus s of n words of space, or even O of z plus s of n words only? Thank you for watching this video.